Hey guys, welcome back to another episode of Simuleos. 1 second, let me change this one. Okay, I should be good to go. Let me go ahead and open up the blinds over here. Let me make sure the camera is set. Seems to be good. Okay, so what are we gonna do today? Well, guys, we're gonna continue working on the Barnes Hut algorithm. Now, here's the thing. This weekend I spent a good bit of time learning a little bit of OpenGL, and I got kind of far, but not nearly as far as I would have liked to get. So, as we start moving on to the visualization, we may need to learn some OpenGL as we're going through. Now, I decided on OpenGL because of a number of different things. I spent like half the day Saturday kind of looking up different things here and there. Cinder, which is the one I was going to use that was suggested by Gustorn, is actually not available on Linux, not so far as I could see, so I did not choose that one. Then I was kind of left between OpenGL and Vulkan. Again, I wanted something that could draw everything kind of dynamically on the fly type of thing. And I figured that since Vulkan cannot be run on a Mac, it's best to just stick with OpenGL for now. Now, I'm not sure how cross-platform all this visualization will be. Again, I have absolutely no way of doing any of this on Windows. So, you know, best case scenario, I can get it working on a Mac and a Linux device. Worst case scenario, I can only get it working on my Linux device. I have no idea how to get it working in Windows. Everyone says it's simple, but we'll see. So I think that's about it. Let me go ahead and open up Xernal, and we'll go ahead and get started. Okay, so what exactly are we doing? Well, first let me move my mic just a little bit. Sorry about that, guys. There we go. Okay, so here's what we're going to do. We are working on an algorithm known as the Barnes Hut algorithm. So let's go ahead and take a look at it. Barnes Hut. Okay, so the Barnes Hut algorithm is a two-dimensional algorithm, or three-dimensional algorithm. Hey Gustorn. 1 second. To do basically an n-body simulator, which means where n can be any number. You basically want to simulate as many particles as physically possible. Now here's the thing. Obviously nature can simulate trillions, billions, as many particles as you want. It has no problem because it doesn't have to do anything. It doesn't have to worry about compute time or any of that kind of stuff. It just does everything on the fly. And that's great, but we're not nature. We've got to use a computer. And so in the act of using a computer, we've got to kind of yeah, we've got to solve some things. Hey, Hypersphere FTW, what's up? So, what are we going to do? Yeah, P versus NP, basically. What we've got to do is basically minimize the number of particles that we're looking at any given at any given moment in time. What do I mean? Well, let's say we have, I don't know, a huge blob of particles over here. I'm just going to draw something like this, and then we're going to put a whole bunch of... You'll have a pretty good life if you manage to pee. Yeah, fair enough. So let's say we have a huge glob of particles over here. Okay? I'm just kind of drawing all the particles inside the circle, but in principle they could be anywhere. Now let's kind of draw a center of mass, which I'm going to put in pink, and I'm going to say is right here. Now again, this is a huge assumption. I have no idea where the center of mass is, but let's just say it's there. Now let's say we have a particle all the way over here. And now let's think. Let's say these particles are under the influence of gravity. So we have force equals gravitational constant times mass of one, mass of the other, over r squared. Okay, so one way we could solve this problem is by taking into account each individual force in here. So we take into account this force, take into account that force, that force, that force, that force. Each of these forces, and forgive me for not drawing appropriate lines, these are all just kind of badly drawn lines, all kind of going the same general direction. We could take into account every single one of the forces. However, this is slow. What we could do instead is take into account just the center of mass. And this would be, well, relatively fast. Obviously, because we've ignored all of the other particles. However, at some point in between fast and slow, we see, well, almost the appropriate physical picture. So down here we see the most physical picture down here, and I apologize, I just realized You guys probably can't see that. So down here, at the slow mark, we have the most physical picture. So let's say physics. But here, we have the best numerical picture, numerics. This means that we can appropriately solve the problem much more efficiently up here. All it needs is a Twitch chat of scientists. We can solve it. That and the fact that you'll be able to break basically every widely used encryption method in polynomial time. Yeah, so, yeah. Forget quantum computing. Okay, so here we have physics down here, the most physical system. Here we have the most numerically friendly system. And in between the two, we have the system that best approximates the physics while not giving up any of the numerical speed. By this, I mean we need to kind of create some parameter that is related to the width of this particular system up here. So the width of this system. And the distance from this system, and we'll call that variable theta, which is often denoted as s over d or whatever. It's basically the width here, s, over d, the distance here. So let's go ahead and erase this d down here, and put it as pink, okay? And that should kind of sort of explain what we're going to do here. The idea is that we have some sort of theta variable that we kind of vary back and forth in order to determine how physical we want our system to be. And obviously, the more physical the system, the better the simulation will turn out in the end. However, the slower it will take. So we're kind of going to be playing this game to see, hey, how fast should we be going? Should we be moving slower? Should we be moving faster? These are all kind of questions that we should ask. And if you've been following my Twitter, you'll note that I did come up with an interesting game that I thought would be kind of fun in order to teach how the Barnset algorithm actually works. Actually, so the quantum proof encryption methods, sorry about that, Gustron, I don't know much about them. Again, it's kind of, I'll be honest, as far as a physicist is concerned, I'm a very bad physicist. I don't know that much about all of the kind of cool physics that everyone's looking forward to. I need to kind of get into that. Okay, so what am I going to say here? So the game's actually relatively simple. You are a star. You press forward with your spacebar, and you kind of move around with your camera, and you move in some direction by accelerating yourself forward, like, well, giving yourself an extra force. You can also change the speed at which everything is moving by changing your theta value. So you can like kind of right click or left click to up or down your theta value. If theta is like super high, then everything's just one glob and you don't see anything. And if the theta value is super low, then you see everything but you're not allowed to move, you know? So the idea is that we can move that theta value up and down to change the speed of the simulation. And your goal is to get to like some red point in space without running into any stars in as little time as possible. So you kind of have to play with the value to find the red dot to begin with, and then you can kind of go from there. This is more computer science than physics, I guess. Yeah, I don't know where this stream lies. I always consider it more physics than computer science, simply because I'm not a computer scientist and I am a physicist. But at the same time, I don't know. I just kind of feel like you're right. This is less physics than I'd like it to be. That said, I always put physics first in the hashtag up top, so just so no one gets the wrong idea when they hop in. This is not necessarily a programming stream. You know, we don't do just programming. We also do physics. Yeah, I just kind of always like to point that out when people come to my channel, that this is definitely just as much physics, at least in my opinion, as it is computer science, but I really don't know where on the spectrum we lie there. Okay, now I don't think there's too much more to discuss here. Honestly, we're kind of sort of doing everything we need. This isn't even like physics? Maybe not, but we are doing physics. Okay, so now here's what we're going to do. Let's talk about how we get from point A to point B. How do we start utilizing that theta value? Well, we do that with something called an octree. Okay, octrees are incredibly cool. We basically implemented them last week, and the idea is relatively simple. Let's say we have a 4-dimensional space, or 2-dimensional space. Sorry about that. And let's draw something called a quad tree. It's the two-dimensional analog of an octree. This is like high school physics. I mean, you're kind of right there, Frank. In some sense, we are just doing, you know, gravitational forces as F equals gmm over r squared. We could, in principle, think of a more complicated way to do gravity, but that requires some crazy mapping that I know nothing about. So, I don't know. Frank, when am I going to do something noob friendly? That's actually a good question. A lot of people come on this channel and they specifically mention, and I get feedback on this channel a lot, about what people want to see. And a lot of people mention that what we're doing on this channel is basically just too difficult to do on a Twitch stream. That's what I've gotten feedback from. Now, that said, I try to keep the simulations understandable. And obviously I do a quick 10-15 minute introduction every day to kind of make it more understandable, get everyone on the same page. But that is a good question, you know? Are we able to, you know, where do we go, you know? But I do want to point this out. I've actually been thinking about turning this one into a game, but that's, I don't know. I don't know if we should. Anyway, I mentioned the game a second ago. Anyway, quad tree, let's go into this. So let's say we have a whole bunch of particles. I'm going to draw the particles in red. Here's the idea. I'm just drawing these particles at random, and of course they could be randomly dispersed. It doesn't matter. Let's try to split this space into even quads. Okay, quadrants. And basically put all of these particles into some place. So let's go ahead and draw a line here. Another one here. Another one here. Another one here. Okay, so this was split into even quadrants and something like this. Okay, well, I kind of cheated here on accident. Something like that. Something like that. Yeah, something like this. Here. There. Here and there. Here. There. Here. There. Okay. So, the idea is that we split the system consistently until we have one particle in every box. Maybe something like this. And we've now created a quad tree. The idea is that each of these leaves, each of the boxes is either completely filled or not filled at all. Now, what we can then do is we can then assume that each of the boxes are, like this, for example, this big box over here is an internal node, whereas this box right here is an external node to a tree. So for example, this tree might look something like this. The root node is the huge box. Then we split it into 4. 1, 2, 3, 4. I can't do the aimbot physics. What time is it right now in Japan? It's 5:13 in the morning. Okay, so then this guy splits into 4. 1, 2, 3, 4. This guy splits into 4. 1, 2, 3, 4. This guy again. 1, 2, 3, 4. 1, 2, 3, 4. Forgive me for the messy trees. Now, let's grab this one. It splits into 4. And this one too splits into 4. Okay, so that's this tree over here. Then we have over here, this guy splitting into 4. This guy splitting into 4. And let's say this guy splitting into 4. And that's our tree. Something like this. 5:13. Why would anyone be preparing for church at 5:13 in the morning? Most church services I was aware of don't start until 7:45 or something in the morning. And even then, it's still kind of early. Usually people have like a, yeah, sorry, the tree's quite ugly. But the idea is that we've tried to represent this as a tree. I apologize for how ugly this one looks. But we have a root node. Then we have all the nodes attached to it. And then we go from there. And what does this allow us to do? Well, let's say we're trying to check this particle here. Okay, so this might correspond to this particle here. Okay, and let's say we're trying to determine the forces on this particle. Well, we check all the particles here, so I'll kind of circle these particles in pink. We check all these particles because they're relatively close. Then we'd kind of go over here to this internal node, and we'd say, okay, well, maybe this internal node is far enough away or close enough that we have to check all of these particles in here. And same with this internal node in here, so we might have to check all these particles in here. but maybe this one's far enough away that we can treat all of these particles as one large particle with a center of mass somewhere around here, if that makes sense. So the idea then is that we can use this node structure in order to determine how far away the particles are and what we can approximate with these particles. Now, what are we doing today? Well, today we've already implemented most of the octree stuff. So that kind of stuff has been kind of sort of done. What we're doing today is implementing the force algorithm. And the force algorithm we're going to be using is the Runge-Kutta method, in particular RK4. Now, I'm assuming that people have seen RK4 somewhere before. But the idea is relatively simple. We're approximating the acceleration as equal to, the velocity as equal to acceleration times time, and the position as equal to the velocity times time. And what we do is we take 4 different approximations here. So we'll say x is going to be equal to x naught, whatever it was before, plus 1/6 times v1 plus 2v2 plus 2v3 plus v4. Okay, and so we take 4 different approximations for v at each different time step. We combine those 4 to create x naught. Now these 4 are kind of iteratively defined based on the acceleration. So we use the acceleration in order to find the velocity, and the velocity in order to find the position at every single time step. We do that 4 times. And then we keep on going from there. We're going to get more into it as we go along. First, let me get a quick sip of water, and let's go ahead and get started with what we currently have. If you guys have questions, obviously let me know. But I spent a good bit of time on Friday going through exactly what it is that we're doing. So I think most of the people who are watching now, probably have seen the RK stuff before. Okay, let me get a quick sip of water. Let me know if you have any questions, and we'll go from there. Frank, are you talking about the American elections? Because Gus Rowan's not from the U.S. Okay. So I'm waiting for just a minute for questions, but I don't see any popping up in chat. So I'm going to go ahead and pop this over to the next desktop and go over here. So let's CD into projects, Simuleos, and of course, where are we? Barnes Hut. There we are. CD into projects, Simuleos, and of course Barnes Hut. Now if we run the last new plot command, let's see. Here is our very latest octree code. He's definitely not Canadian. So you'll see that we have a whole bunch of red particles in the center there. Maybe this is the best way to do it. I guess this is an orthographic projection or something like that. Okay. Here we have all the particles, and here is our quad tree. Two of the 3 dimensions of our octree. If we move down here, we see another of our dimensions of the octree. Something like this. Let's see if we can get this right. Over there. Okay, and of course we can turn this way to see the other dimension. Something like this. Now, this means that we have our octree probably working. In fact, we checked it last time with a simple case, and it seemed to be working just fine. Some of the cases don't look quite right, like this one here. But if you kind of look at it in all dimensions, you kind of see where all the particles are fitting. And it seems like they do fit quite well. So, I think the octree code is currently working. I'm fairly confident in saying that it's working. So now it's just a matter, let me see here. Now it's just a matter of finding how the forces act between the particles. So here's where we have to implement the RK4 stuff. So, we are significantly far along. I'm quite happy with bad season, playing other countries in Europe, can't talk English properly, can't speak English properly, yeah, sure. No, the issue is, I mean, everyone has kind of a different way to speak English, right? I mean, like, look at the difference between UK and Australia and the US, you know? Everyone has a different accent. So it's kind of weird, but I don't know. Other countries can't be bothered to spell correctly. I don't think that's true. Anyway, let me go ahead and grab my notebook, and then we'll get started with the RK4 stuff. Oh, also, I told you I spent this weekend learning OpenGL, right? I spent an abnormally long amount of time just trying to figure out how to draw a sphere in OpenGL. I didn't quite get to it, but I think I have an algorithm that will kind of generate the triangles on the fly. Now, I could do this in a number of ways. There's a number of algorithms I could have chosen, and in fact, I have some up. Let me see. Here is my... Here. So I have a couple of different algorithms up. Here's one there. Here's one there. But I didn't like either of these algorithms for a number of reasons. This one is closest to the one that I was going to use. So I kind of just made one up, and I think it's going to work. I'd like to try it. Worst case scenario, it doesn't work, and we go from there. Fixed function pipeline or shaders. What I was planning to do was, let me think. It's been a while. It hasn't been a while. I did it just yesterday, but I'm so newbie with it. Like, I just don't know what I'm doing exactly. Who am I voting for in November? That isn't really much of a question considering I'm a scientist and one of the parties is clearly anti-science at this point. As much as I hate to admit it, there isn't really much of an option here. Have you called GL Draw? Kind of. We've drawn it. I have not drawn this yet. I've simply done two-dimensional shapes. Here, let me show you how bad I am at OpenGL right now. Here, let's go ahead and CD into projects. One second. CD, back a couple directories into projects. Tests. Where am I? That was 3 dots. Tests. And then we go into OpenGL. Let me just run the make command. This is as far as I got. I know it's pretty crappy, but this is as far as I got. And that's as far as I could get. But it's pretty far, I think. I mean, we got our make file and everything set. I think it's far enough that we can figure everything out on the way, and we'll go from there. Yeah, sure. VI, 1 second. What is it? It's not make sphere. That's the broken one. I think it's simplegl.cpp. Okay. Draw. So, let me see. I guess we're not using GL Draw for this one. Sorry about that. But here's our loop where we're kind of doing everything. Let me see. A couple questions. Yeah, I'm sorry about that, guys. I can't vote for Trump. I don't really like Hillary that much. Bernie was okay in that I could trust him. But I don't know. It's just a rough situation in the US right now. How complicated is voting for you where you are at the moment? It's not so bad. I just have to send in a request that says, you know, it's an absentee ballot. I just have to send in an absentee ballot. So that's all I've got to do. Yeah, that's currently what I'm doing. 1 second, let me think. I was following this guy. This was the guide I was following. Yeah. So, we can spend some more time working on this. Sorry about that. Yeah, I kind of do. I don't really, you know, I'm not really a Democrat, and I'm not really a Republican. When it comes to that kind of stuff, I really am somewhere in the middle between the two. On the one hand, I don't really want to get into politics on the channel. Sorry about that. I end up rambling about politics all the time just because it's something to talk about. I got my hair cut a while ago, but I guess it's been, let's see, I think I got it cut last Wednesday. Then I did a Thursday and Friday stream. Then I took 2 days off because it was a weekend, yada yada. So yeah, I guess my hair might have been cut since the last time you saw me. Trump is bribed, James. You know what? He might be. He might be. Okay, so we'll keep working on the OpenGL stuff as we get to it. I don't expect to get to it today, though. I think we'll get to it either tomorrow or the next day. So let's go ahead and CD back a couple directories. Okay, that wasn't what I meant. Then we go into Simuleos and Barnes Hut. Okay, so what are we going to do here? Let's go ahead and open up the Barnes Hut.cpp file. And let's see what we got. So going through the file here, we have a good amount of stuff that we've done so far. Let me go ahead and open up my my notes here. Every once in a while I have to write notes. Not saying that writing notes is a bad thing. It's just most of the time I don't. Okay, so what do we have here? We've got a couple of different guides that I have written down. Implement theta, force integration, visualization. Back then I was saying OGL Blender or VTK. I kind of ditched VTK after looking at it. Not because it was a bad system, it's just it won't... it's a little bit weird for what we need to do. So right now we just have the simple nuplot stuff. That's okay. OpenGL I think is what we'll go with, but we might try Blender out first just to see how it goes. Okay, now how does this algorithm work? Or how does this code work? Well, we have our struct particle here, which kind of holds a whole bunch of stuff. Mass, radius, and the vector position, which is an XYZ coordinate, basically. Now, one thing we're going to have to add in is we're going to have to add in a new vector here. So let me think. We're going to have to add in a vector for acceleration and a vector for velocity. Okay. Wait, it's people like James here that are going away from the USA trying to ruin the country. Oh, yeah, definitely, Frank, don't... Yeah. No. That last comment wasn't racism. 2 comments up when you mentioned Mexicans in your country, that's racism. Definitely don't say that. Be careful. Okay. What do we do here? Particle, mass. Okay, so now we have this guy being generated. And let me just go ahead and run this code real quick. So Control D, write this. Now let me think, do we have any header files in here? I think we have been compiling it from, yeah, I think we've just been compiling this standard. The G++ Barnes Hut .cpp we have, okay. And if we run a.out, everything seems fine. Good. I feel like, yeah, I can take a look at the link. See what we got here. Open link. Nation of the world with Trump. Huh. Fair enough. Coming from Animaniacs, I guess. Okay. So we have the acceleration and velocity. We need to add an acceleration and velocity for the RK4 algorithm. Now let's think about how we want to implement this. We need to do a couple of different things here. We need to implement a function that will give us the force acting on any given particle, right? So we need basically a function that takes in a particle, goes through the tree that we've generated, and then, after going through the tree, basically tells us how the acceleration has changed. This is kind of like creating a force diagram, right? So the idea is that we have a mass of the particle, and a mass of all the other particles that we're working with. So then it's just a matter of basically adding all the forces together. So we'd add all the accelerations up. I think that's the best way to go to start, and then perform RK4 after getting the acceleration on the particle. Let me think, is that the best way to do it? That's assuming that the acceleration is constant. Maybe there's another way to do it, but that's currently how I'm thinking about it. So create basically a force diagram, add all of the forces together, find the new acceleration, then after finding the new acceleration, go from there. So what do we need to do? We need to create a function to do just that. So let's go down here and create our function. Function to find acceleration. Oh wow, that what was I trying to spell there? Acceleration. Is that right? Yeah, sure, why not? Of particle in Barnes Hut tree. Yeah, wall are fun too. You can shoot people who try to cross them. That's not as fun as it might sound. Yeah. I mean, here's the thing. Trump's wall is not going to go up. I mean, there's just no way. I misspelled function too. It's one of those things that, I mean, I don't understand how and why it's such a big thing. Why so many people want this wall. It doesn't make any sense to me. Spark88, which university did you graduate from? I graduated from Auburn University in the United States, Alabama in particular. I'm now at the Okinawa Institute of Science and Technology. There's some links down below in my little notation biography thing. Feel free to click on those if you're interested. But yeah, it's a little bit too early for the OIST advertisement today. So let's do that. What are we going to call the function? I guess the function will be called force integrate. Let me think. So we go through root. Let me think. You're blinded by the Japanese. They bring drugs with them. I think the Japanese are one of the least druggy nations. Like, it's pretty... It's worse than the U.S. over here in terms of, you know, their acceptance of even marijuana and stuff like that. Okay, China built a wall. They sure did. Okay, so let me think. What are we going to call this? I guess we'll call it Void Force Integrate or something like that. It's not quite RK4 what we're doing right now. So let's think about how we want to do this. Let's go ahead and read in the root node. So what are we going to say? We're going to say node root. Okay. So what's the idea here? We're going to go through each of the particles. We're going to perform a depth first search traversal for each of these particles. And then after that, we're going to... oh, I see. Thanks, Custron. Then what we're going to do is after that, we're going to go through each of the individual particles and basically perform a depth first search traversal and figure out what's it acting on every other... what is acting on this one particle we're looking at. I don't think this should be too difficult to write, but we'll see what happens. Again, I have it kind of in my mind how I want it to be written, but as always, I kind of wait until stream to actually do the writing. You know, my philosophy with this is the exact same philosophy as people who do like, not like Let's Plays, but more like people who do blind playthroughs in a way. They kind of have the idea in mind of how to kind of get through something, and then they implement it the day of, you know? So like, I kind of like the idea that some of this is at least on the fly, so we can work with each other. Recursive chat, is this C? Yeah, it is C++. We are currently using... Let me see. Yeah, nothing but standard libraries in C++ and a vector.h file which Gustorn has generously written. Okay, so what are we going to do here? Okay, so first we need to go through all the particles. If we go to our node, let me go to the top, struct particles, struct node, you'll see that we have basically an array of particles. Where are we? Vector particle pvec. Okay, so we'll go through there. Thanks, Threader. Okay, so let's go through all of these. So we're going to say for auto I in, let's say, how about let's not call it I, let's call it, I don't want to call it P because P is position, so let's call it particle. Part's okay. In, then we're going to say root.pvec. So now we're going to be going through all the particles. And guys, feel free if you see any typos or anything like that. Again, it's 5:33 in the morning. I use that as an excuse every single day, but hey, sometimes if the boot fits, you kind of go with it, right? Okay, so now we're going to go through each of the particles. What do we need to do? Well, with each of the particles, we basically need to read in that particle's location. And then, from that particle's location, we need to go, also go into our depth first search traversal. C-like mindset basically means, and I don't know if you can hear the audio recursive chat. I would imagine you can, but a C-like mindset basically means that I'm not using all of the latest and greatest features that C++ has available. Quite frankly, it's easier for me to understand C than it is C++, just because I'm coming from a numerical physics background and not a computer science background. Which means there are some C++ features that I ignore, and I kind of stick to a C mindset, which is easier for me to understand. Now, that said, I've been trying to get better, but it's still, you'll notice that as I'm coding that I'll do things that are a little bit differently than someone who has been trained in computer science would do. So just kind of keep that in mind. If you see something and you think there's a more efficient way to do it, of course, I'd love for you to say it in chat, because when you say it in chat, I can kind of think about it and we can kind of work on the algorithm together. So here's what I'm going to do. I'm going to say going through particles in pvec. No, I don't use, well, okay. We do use pointers every now and again, but we don't use them that often. Recursive chat, mainly free functions over member functions. Usually C-style APIs, generally not using latest and greatest C++. Yeah, that's it. 24 years to C++, unless I like to use C++ features. Yeah, fair enough. I use pointers in my my research code simply because, let me think, for For CUDA stuff. Yeah, CUDA stuff. It's really kind of annoying. Gosh darn it. With the CUDA stuff, it's you aren't able to read in vectors. You have to read in kind of pointers and stuff. So that's what I have to do. Can you please tell about your university again? Sure, yeah, I love talking about OIST. The Okinawa Institute of Science and Technology is located in Okinawa, Japan. There's actually a link directly under my stream, so feel free to go to info. Scroll down somewhere in here, chat rules, feedback, auxiliary info. Here it is. The Okinawa Institute of Science and Technology. It brings you to admissions.oist.jp just because this kind of gives you an idea of like the PhD program and stuff like that. But it's a pretty good link. I'll go ahead and give it to you guys here. But again, the idea here is that it's in Japan. Let me see. It's in Japan, but no one here really speaks Japanese. It's an English institution in Japan, filled with international collaborations basically everywhere. Like my lab in particular has no one from Japanese. And then we'll go from there. Dang it, Gus Jordan. Anyway, if you're interested in graduate school, feel free to apply to OIST. It's pretty cool. My previous institution was the Auburn University in Alabama. It's pretty cool. It's not particularly known for physics. I did basically plasma physics there. If you're interested in that, let me see. It's known as a cow college for a number of different reasons. Yeah. Hey, Husky. Yeah, everyone makes the moist joke. Most people make the moist joke. So yeah, if you're interested in Auburn, feel free to go there. It's known mainly for football, not for academics. But it does have a decent enough physics department. It's known for engineering in the South. So it's pretty good. If you're interested and you are from the Southern United States, maybe take a look at it. Okay, so now we're going to go through all the particles in PVEC. What are we going to have to read in? Well, we're going to have to do something kind of like this. So let's say we have our force integration. Roll Tide. It's actually weird. For some reason, every time I say I'm from Auburn, everyone's immediate reaction is Roll Tide. I'm like, no, that's the wrong college. You know, and I think they're doing it to troll me, which is fair enough. But you know, I don't know for sure because I'll say it here in Japan where people definitely don't know, you know, what the difference is between, you know, Auburn and Alabama. I'll say I'm from Alabama, and every once in a while someone who's from the US who happens to also be here will say Roll Tide, and I don't know if they're trolling me or not. So I just kind of like, yeah, wrong college, and just kind of awkwardly say that. Okay, so we're going through all the particles. We're going to need some sort of function here, and this function here will be, let me see, we have force integrate. Let me think. How do we want to do this? I guess we'll say RK search or something. And forgive me for the name. We'll kind of go through here in a bit. What we're going to have to do is read in the root node. Then we're going to have to read in our theta value. 1 second. And then we're going to have to read in the particle position. So we say part.p. Okay? Something like this is what we need to do. Now, let me think. We have go through all the particles. So I assume that we'd be reading in our theta value here. So double theta. I feel like unless you actually Roll Tide is a troll. Maybe. Okay, so let me think. I'm going to have to go down here to main. Go up a little bit. Add in double theta. Now, again, theta is that constant that we were talking about before. 1 second, double theta. Theta is that constant we were talking about before that's basically related to the width of the object we're looking at over its distance from the particle. We're asking for the force 4, if that makes sense. And of course, if you guys have questions, just let me know. Okay, so what are we going to do? This is kind of how I'm imagining this is going to go. We're going to do an RK search. And this RK search is going to modify our particle P. Then we're going to do an integration here. So we're going to say, well, basically exactly what you'd expect. We'd perform RK4 of our particle P. Okay. Now, we could do this in a number of different ways. Particle position. I guess it's not particle position, it's just particle here. Okay, so every particle now has an acceleration and a velocity associated with it, right? So, we should be able to go through, search for all the particles, modify their positions based on our Runge-Kutta algorithm, and go from there. Now, I don't know the best way to name everything, and I apologize for that. If you guys can think of better names, feel free to do so. My thing is, though, I think we want to do this in 2 different loops. Reason being that we take a snapshot of all the particles, and then we actually perform the integration of each of the particles. So I think in the end I want it to be this way. So going through all the particles in PVEC, finding the new acceleration. Okay. I know a better name, James. What is the better name? And then we're going to say, going through all the particles and updating position. Okay, so we're going to go down here and we're going to say for, just like we did before, auto part in Zadiston. Come on, root.pvec. That is a little racist. But I think he's trolling you, Frank. I'm not sure. Anyway, again, try to keep that down. Okay, so what are we going to do here? So then we say RK4 of the particle. Something like this is kind of what I'm imagining. Nah, mate? Okay, so let's just kind of implement these functions as I'm kind of imagining them now. And as we kind of get through, we need to kind of think about how these will be written and everything. Gosh darn it, I'm so tired. Okay, so let's go ahead and write the functions down here, and then we'll update the tag down there. So we'll say function to find, I guess, acceleration of particle in Barnes hut in tree. And I realize that's the same, I suppose, comment that we have up here. So we should probably update that comment. How do I always misspell function every single time? So we're going to say rk search. So we're going to say void rk search. And again, there's many different ways to do this. So feel free to do this as you will. We need node star, we need theta, and we need part.p. Okay. Okay, so this is going to be a double. 1 second. And this is not going to be part P. This is going to be a vector. And we're going to say position here, just so we don't get confused. And this is going to be recursive function. 1 second. Let me see. To find acceleration particle in tree. Let's go here. Let me see. 6970. But we've been over this 2 days ago. That thing, and you got your coffee machine. I'm not sure what you mean, Frank, but that's okay. Let's go down here and let's say void rk4. And again, definitely better ways to do this. This is just what I'm thinking about now. So it's gonna be particle part. Okay. Now again, the particle has the velocity, the acceleration, everything like that. So this is going to be actual implementation of Runge-Kutta for method. And I know what you're thinking. Why are we using 4 instead of 2, or I suppose 8 is the next one up? I'm not sure, but maybe 6. I don't know what the next one's up is, but I think it's 8. Regardless, the reason we're using 4 is just because it's in general what people use. I see RK4 used more than I see any of the others. We could use RK2 if we're worried about speed or anything like that. And in fact, we could just go ahead and write an RK2 along with the RK4. But for now, I think this is okay. So what I'm going to do here is I'm going to write a quick note. Note, it assumed that, how do I put that? It's assumed that all particles have already updated their acceleration. Okay, so let's go ahead and grab these functions, put them up top, just under the force integrate function. So let's go up to main, and let's put them right here. Okay, so let's go ahead and, you know what? I've realized something. I say let's go ahead and do this so freaking frequently. Is that, anyway, I say it a lot. I need to kind of tone down how many times I say let's go ahead and do this. So let's say RK search. This is going to be a recursive algorithm, right? So the idea is that we start at the top of the tree, and we basically check to say, we find a new theta at every point, and we go from there. So this shouldn't be so bad. So let's say double theta. Theta, I guess we'll say 2. I don't really like that, but that's okay. Are you reconstructing the octree every iteration of the simulation? No, wait. Yeah, after the positions have been updated, we're gonna have to reconstruct the octree. Yeah, we will have to, I think. But that's okay. We'll kind of hit that as we hit it. Yeah, we're definitely gonna have to reconstruct the octree. Unless you can think of another way to do it. If you can think of another way to do it, let me know. So here's theta 2. And how about we call it... This isn't exactly the easiest to think about now that I think about it. But easiest to think about now that I think about it? That doesn't make any sense. Okay, so we started the root node. Oh gosh. Force integrate. Current is what I want. There we go. Let me go to the top. And let me update that again because I just realized that was my bad. I forgot to add a current node, which is a node that we're currently on. I mean, let me think. But how would you do this without reconstructing the octree? I don't know how to do that. Is there a way to manipulate the nodes of the octree such that we don't have to reconstruct it? I mean, we could assume small variants, and then we'd only have to reconstruct internal nodes. I don't know. I don't know how to think about it. This thing is meant to simulate stellar dynamics? Kind of in a way. I mean, it says that most of the time when people do this type of simulation, it's to do very large-scale simulation. So it's usually for like stars and galaxies and stuff like that. We'll kind of see how that goes. So let's go ahead and... I said let's go ahead again. Okay, so let's do this. So we're going to say defining new theta of current node. Okay, so we're going to say theta 2, let's do it, is going to be equal to, and what do we want here? We want basically the width of our node that we're currently working with divided by the distance from the center of mass that we're currently at. And yeah, let me see. Is this right? Is it 1 over? Let me think. I have to think about this one. This is going to define some sort of threshold, right? So let's say let's think about how this theta needs to be. So I've written down S over D. I'm going to assume that it's something like this. So I'm going to assume it's going to be current dot box length, which again is a double, divided by distance between position and current dot center of mass dot position. I think that's right. Let me go to the top and let me check. COM. There's one. Yes, so we need the COM dot position. So I think the distance worked with this, and I think that should be okay. To be clear, let me go ahead and go here, and let's run the last G++ command. Okay, so I have a couple of issues here. Let me see. 365. For root pointing to p back. Oh, that's because these need to be arrows. Every time I do this, pointing to. Then what do we want to do down here? We're going to do pointing to. Let me think. This needs to be pointing to. And I think... Oh, my bad, guys. Here. G++. Good, that one runs now. Also, I would have the money to buy a new PC, but why would I? The current ones serve me well, and I'm over upgrading my phone, PC, etc. just because a few years have passed. Honestly, that's totally right. I mean, let me think. My father was a big person on... nothing's wrong with my father, for the record. But he was really big on the whole, computers only last a few years, you buy a new one, you throw the old one away, you know? But here's the thing, I can't pull it out, but I have computers that are like... My first computer I bought when I was just coming out of junior high still works just fine. No reason for me to get a new one, because for what I need it for, which is just SSHing into other machines and using those machines, it works perfectly fine. Now, sure, it's missing a battery, but with Arch Linux on it, it's not like it's slowing down any. And it's quite nice to kind of keep old computers, in my opinion. Yes, I have 32 gigabytes of RAM. I could update that to have more, but in fact, I was watching this gaming streamer. His name's Psycho, and he was mentioning that he got 128 gigabytes of RAM. 128 gigabytes of RAM. Why would you need that? Like, maybe it wasn't DDR4, maybe it was DDR3, but even so, that's still a lot of RAM. Anyway, so we have this as our theta 2, and here's what we're going to do. We are going to say, as we're traversing this tree, we're going to say, sorry, I bought a high-spec machine. I'm not anticipating changing this machine out for a very long time. It's what I've got. It is my machine. I'm not, when I move, I leave Japan, this machine's coming with me. Okay, so now what do we need to do? We need to, 1 second. Honestly, I totally agree, Novelist. I mean, the thing is, I'm always on some sort of cluster or something like that off the side. I don't normally work on my own machine anymore, Every once in a while, I'll have to pull up a graph or something like that, but usually that's, I use SSH-X or something like that. 128 gigabytes? Oh, wait, what do you mean, happy little rat? I'm not sure I fully understand what you mean by maximum supported by Windows. Oh, are we talking about RAM? Wait, what? Oh, 128 gigabytes of RAM is the most supported by Windows. Maybe that's it. Let me see. You bought in Japan as well? I did, actually. Yeah, I totally bought it in Japan. Okay, so let's keep going from here. We need to find the acceleration. Acceleration. Due to the particle. Something like this. Find the new acceleration of particle due to, let's say current node. Okay, so let's see. I use packed pointers in my engine that supports up to 256 gigabytes of addressable space. Oh, fair enough. Nice one. Japan has high tax imports? Maybe, I'm not sure. Honestly, I went to Amazon.jp and I just bought stuff. Okay, so what are we doing here? Let's see. Well, we want to make sure we don't double count anything. That's one thing we want to make sure we don't do. So let's say we have an internal node. What are we going to say? If that internal node, let's say the theta for that internal node is underneath theta. What do I mean by that? So I guess we'll do something like this. We have our theta. Yeah, okay. Let me see. I'm missing something. I want to get the White Fox keyboard, but the mass drop has ended. Are you simply destroying particles that go outside the octree bounds? No, the octree can be as large as we want. Where do you find books or blogs in open access? Or can you recommend SMH? I did not put a review for the 970. However, Spark, for open access, there are a few journals that I know about. In particular, though, if you're looking for good research that's open and free, feel free to go to the archive. The archive is absolutely awesome. Like, this place is where you find so much information. I don't know if this is exactly what you meant, but I definitely like to support the archive whenever I can, because they, this is where people put all of their preprints. So if you're looking for articles that are just out there in the public that you want to learn about, just go to the archive and I can guarantee you'll find something. For example, for me, I can go to like computational physics, or I can go to, where is it, quantum physics here, and I can find a lot of stuff for what I need. Oh yeah, honestly, I'm really looking forward to that. I'm gonna be honest, I am a huge proponent. Like, I love the idea of having every article be open source, and here's the reason why. Within the scientific community, you can find pretty much any article you want available to you, right? Like, you can find anything from Nature, from PRL, from Physical Review Letters A through E. You can find anything you want pretty easily. because you're part of a network, and that network gives you access to all of the journal repositories. However, if you're not a part of that network, you can't have access to those journal repositories. Rather, you have to pay for every one of those articles. And though oftentimes it's not expensive, there is a paywall there. And one thing that drives me nuts is that a lot of people are very ignorant about how science works. And I always sit there and think to myself first, why don't you just read the article about this particular topic? Like, you know, climate change and stuff, surely someone is smart enough to read through all the articles. And that's the thing, people are definitely smart enough to do just that. However, they can't, because it's behind a paywall. So if everything's open access, we can then really start to give people the papers and say, hey, look, it's not just a study, it's this study in particular that shows this. And that's pretty useful. I've done gravitational simulation before, and there are times when stuff gets flung into far reaches of space. So you'll definitely have stuff going outside the octave bounds. Yeah, so that's the thing. I'm not going to bound it for the first little bit. We'll see how it goes. We might have to. We'll see. Okay. Let me actually put that up in notes. So note. Gosh darn it, my nose is so itchy. We may to ignore particles are too far away. Okay, let's go down here. What can we do? Oh yeah, that drives me nuts too. Like they'll give you, they'll give you the algorithm. They'll say like, oh, this is so cool. It does this and this, and you're like, oh, that's great. And then they're like, implement it yourself, and I'm like, ah, darn it. I take $50 to access ACM articles, so I don't read them. That's the problem. I can't read it. Fair enough. I mean, here's what I was thinking, guys. I don't know if you guys would appreciate this or not, but I really have been thinking about just Saturday mornings, getting up and doing like a journal club for this stream. I posted that on Twitter. I don't think it got any responses. I didn't check this morning though. Yeah, so we just take an open access article. I'd go through it and we'd basically just talk about it for an hour, and that would be it. Like that's the entire stream of the day. Just going through a journal article that happens to be open access, you know? I thought it could be kind of fun, but I don't know, it's kind of up to you guys. It would kind of help a lot of people in kind of going through the process of understanding a paper. But it's kind of up to you guys. If you want to, if you guys want that, let me know. And I think it'd be kind of fun. A lot of the articles can, but I kind of like to stick to things that are on like the archive or something like that. Anyway, let's go through here. Let's see if we can figure this out. So, let me pop over here, and let me do page, new page before. Journal club. I don't know how to make it. I need some sort of like alliteration here. I can't think of one. Saturday. Saturday. Social Saturday? No, that doesn't make any sense. Okay. So here, let's draw a octree here. Let me try that again. Okay, here we have, whatever, it's a box. It is a box. Pretend it's a box, guys. Deal with it. James, why don't you use a Mac? I'm using Mac for iOS dev. Honestly, I use a Mac at work. It's not so bad. I just don't want to use it at home because I like Linux. It works quite well for everything I need it to do. Now let's draw an internal node here. Okay, so if we have a particle here, and we have an internal node here, which is what we're currently going through, we're going to check theta. Theta is going to be equal to, I'm going to draw it in green here, S over, let's draw it in bright blue, distance here, okay? I'm not an Apple fanboy. Okay. So we've S over distance, where this is what we've defined. Now, how do we know whether we check, like, how do we update this acceleration? So we know that force is equal to mass times acceleration, and it's going to be equal to g times the mass of one, mass of the other, over r squared. This means the acceleration is going to be equal to gm over r squared, where m is the mass of this object over here. That's fine. That's not the hard part. The hard part now is deciding whether an internal node or an external node, whether we need to check the internal or external node. I actually don't have a phone. I don't use a phone at all. So, nice try there, Frank. Okay, so here's the acceleration. That's not going to be hard. Now, let's say we're at this internal node. The question is, do we take this internal node as an internal node? Or do we treat it as the external nodes that come on the inside? Well, I guess what we do is we do this. We'd say, okay, let's say this theta. We read in some theta, and we say this theta, we called it what, theta 2 or something like that? If this theta 2 is less than our theta, let me think. That's basically what I did. I mean, here's the thing. I'm on a subtropical island off the coast of Japan, right? Under what situation am I going to need a phone? Who am I going to call? Ghostbusters? I mean, come on. Everything I need is going to be found via Google Maps. There's some people at Oyster I could call here and there. But for the most part, if I'm stuck, I'm stuck. There isn't really much I can do, you know? Besides which, I really go out so little that under what situation would I actually need to call anyone? Like, it just doesn't make sense to me. How am I going to call my mother? I can't call my mom. She's in the US. I mean, what am I going to do? Just like, I could call her via Skype. That works. Anyway, so theta 2 less than theta. And that means we're within our threshold. I just use Skype or Google Hangouts or something like that. Let's see. Is it supposed to be less than or greater than? I'm actually not sure. Anyway, if we compare it to this theta, then we check the internal nodes, and then we keep comparing the theta, and I guess we only count. Yeah, I know what we're gonna do. We only count the node if we are above the threshold. There we go, we're set. And then we do a recursive search otherwise. Yeah, that's a good idea. Problem solved. Okay, so find the new acceleration here. So we're gonna say if, what are we gonna say? Theta 2 is greater than, let's say theta, which is the one that we're reading in. We're gonna do this. 1 second. Else this. Now the question is it greater than or less than? Let me think. What is this physically representing, this theta? We're saying its current box length is the size of... Yeah, wait, what's wrong with that? Frank, what is wrong with having a face-to-face conversation on Google Hangouts? I don't think there's anything wrong with that. I think that's fine. Perfectly fine. We usually use Skype because my mom knows how to use Skype and doesn't know how to use Google Hangouts, but that's still fine, you know? Okay, so if theta 2 is greater than theta, here's the question. What does that mean physically? So let's take a look. As we said before, S here is the size of the internal node. I suppose if theta is super duper small, that would mean that either the distance is really, really high, it's super far away, or the radius is really, really small, right? So this would be a situation where we would not want to treat the object that we're looking at as a particle, right? Please stop with the RAM. So in this case, where theta is really, really small, we don't want to treat this node as a particle anymore. So I'm going to say that if we are less than the threshold, we're going to go ahead and add the acceleration for that particle. But if we're greater than the threshold, we're going to do another recursive search. This is what I'm currently thinking, right? So this means that, let's say we are at this internal node here. If we are under the threshold, yeah, that should work. This should work. I think this should work. So we'll say this less than, and then we'll go down here. What's the worst that could happen? Okay, so now we have to find the new acceleration. So we're going to say double acceleration. Oh, how about vec acceleration? is going to be equal to gmm over r squared. So we have to find the gravitational constant. Now the question is, how physical do we want to be here? That's a good question. I don't have an answer to that. Let me see. So what is G? G is... Yeah, so let's go down here and let's say G. Gravitational constant. Let's stick with physical limits for now. So let's go in here. Let's see. So I'm going to define this as a constant, actually. So let me go up to the top. Let me see. Do we have... Here it is. So let's say constant double. Oh, my bad. Constant double particle. Gravitational constant. That's super large. Yeah, that's exactly what this algorithm's doing, right? So we ignore any of the nodes that we don't need to look at. Gravitational constant equals... It's pretty tiny. 6.6748 e to the negative 11th. Let's grab this. It's not the tiniest thing, obviously. I mean, I'm used to dealing with things times 10 to the negative 32 because of my work. And let's see if we can... Gravitational constant is such a long, thing. Like, surely there's a way to shorten this up. Why don't we just change it to... Everyone just calls it G. No one look. Okay, so we're going to say vector acceleration is going to be equal to... something like this, we'll modify it. It should be G times the mass of the particle that we're looking at here. So it should be current dot center mass. Dot mass over distance squared. So let's go over here and let's kind of look at it. I've actually never done that. I need to look up this archive. I'll do that in a bit. So let's go up here and define some stuff. So actually, that would be super generous if you wanted to, Frank. Although I don't take donations. So let's defining a few variables. So we're gonna say r double. Oh, it's actually a vector, isn't it? No, it's a double. Double r is gonna be equal to distance between the current position and the current pointing to center of mass position. Okay. Add in a semicolon there, go down here, change this to R. I don't know what your problem is with Gustron. He's like a super nice guy, Frank. Seriously, lighten up. Okay, so let's do this. Vector acceleration G current mass divided by R times R. Something like this. Okay, now the problem is this is not exactly X, Y, and Z friendly, I don't think. So let me see. G, current mass, RR. What is R? So then we need to split this up into the X, Y, and Z components. So let me think real quick. So we can find the acceleration. Then we have to basically split up in X, Y, and Z for direction, right? That shouldn't be so bad. So we'll say this, we'll say double acceleration, and work with that. Well, the only problem is... Wait, what is Wessex? I don't even know what that is. Okay. So double acceleration here. Now we have to find, let me see. Basically the X, Y, and Z position here. So let's go through and let's say this. We're going to say... Oh, wait a minute. Do a theta squared comparison instead? I'll think about it. So let me see. I also just realized I have to read in something else here. And I apologize for that, guys. I'm kind of going through this on the fly. So let me go up here. And let me see. Instead of this being a vector position, I think we need to read in... Yeah, okay, so let's do vector position here. But actually, instead of reading in a vector position, I'm thinking we want to read in another node here. So how about we read in node star, instead of current, we want to read in node star. The problem with it is Happy Little Rat, he's actually got like 12 accounts. He's like Frank3434, Frank34345, Frank34344, lots of accounts. So it's kind of, he's all over the place. Okay, so now we say node star. And what do I want to call this node? We'll call it, should be particle at? Where? I'm not sure. How about we say node? Man, this is actually kind of a pain for naming. Let me think. Let's say particle. Should be okay. Should be okay. You're traversing the octree and adding acceleration to the particle. Yep. Wait 1 second, let me think. For auto part in root pvec, yeah, so we have part position that we're reading in, but it is particle actually that we're going through. So it should be particle. You're right. Yep, you're right. I'm wrong. So particle, part. You guys are right. Particle ampersand. Okay, so then we're going to go down here. We're going to say particle dot position. And that should be it. Good. Sorry, Zadson, I misunderstood what you were saying, but you're totally right. Let me go up to the RK search real quick. Let's fix that up. Here we are. It's taking a lot longer than I was expecting. My apologies, guys. So let's say part, ampersand part. Go down to the bottom. Okay. So now we have this. Again, we can debate about the R squared thing. That's something we can look at. But for now, let's just kind of think about how we want to do this. So we'll say double acceleration is going to be equal to that. Now what do we say? We need to split this up into an x, y, and z. So what we'll say is particle dot x is going to, we're going to add on. Okay. Now, how do we split it up into x, y, and z? Well, currently we're in spherical coordinates, right? And we know that since we're in spherical coordinates, new page before. And again, maybe you guys have a more efficient way to do this, but here's how I'm currently thinking about doing it. So we have particle here, particle here. We're in spherical coordinates, we'll say. I don't really know what I was trying to draw there. I think I was trying to draw a line, but it really didn't look like a line. So now let's draw a line here. And then let's go there. Okay. So to go from spherical coordinates. Yeah, well, kind of. Because right now all we have is this R value. So we're kind of in spherical coordinates at this point. We need to go from R into an X, Y, Z. Because we have an R. That's all we have. We have an R and we have an acceleration. So because we only have an R, it's automatically in spherical coordinates. Yeah. So now we have to convert this into an x, y, z. So we'll say x is going to be equal to, let me think here. Now you guys are kind of confusing me. Are we not? Let me think. So how do we convert this into Cartesian? Well, what we can do, yeah, we have a distance vector. Oh, do we have a distance vector? I thought we just had a distance double. 1 second. Let me take a look. If we have a distance vector, then we should be fine. But I thought we only had a double. Let me check. I could think of another way to do this. Let me think. Let's think of another way to do this then. If you guys aren't confident with... it's definitely currently in spherical coordinates the way I've written it down right now. Definitely in spherical coordinates. Because all we have is an R. R is the length of the distance vector. Let me think. So we have, let me take a look over here. So let's go into vi vec.h. And let's go down to distance. So we said length. What is length? Length is dot on the left-hand side. Here we are. Vector distance is current position minus particle position. Double R is length of D. You really shouldn't use zero coordinates. I know it's going to kill the performance, but we're currently in spherical coordinates. That's what I'm saying. Like, we have an R, so we're obviously in spherical coordinates. However, if there's a way to grab the distance vector in another way, as I said, there might be a more efficient way to do it. Let's think about it. So, what you're saying is we can find a difference between X, Y, and Z. That should be okay. That will give us a distance along X, Y, and Z. Then what we can do... Yeah, we can find the two angles relatively straightforwardly. Let me think. I'm trying to think of how to do this without converting it to spherical coordinates and back. And I'm not currently sure how to do that. I have to think about it. So, okay, let's say we have... Okay. Let's say we have X, Y, and Z. So we'll have a difference between X, Y, and Z here. So let me just do page, new page before. Or after, whatever. So we'll have, let's say, X1 minus X2, Y1 minus Y2, Z1 minus Z2, okay? Okay, so we have these three values. Vector D is current center mass position minus particle position. Double R is length of D. Okay, so then we have these guys. This will give us basically X, Y, and Z. One second. This will give us X, Y, and Z. Now, how do we turn this into an acceleration in X, Y, and Z? One second. So we know that R squared is going to be equal to the square root of X squared. I'm sorry, it's going to be equal to X squared plus Y squared plus Z squared, right? So we find the acceleration. Then we know, hey, I care. So we find the acceleration. Then we know we can split this up into the different vectors relatively easily, right? So we could say, we could say the acceleration dot x is going to be equal to the acceleration. Let me see, square root of the acceleration total. One second. Yeah, acceleration total minus acceleration dot y minus acceleration dot z squared. Yeah, or we could do that. Let me see. So we'd normalize it. Okay, so now let's think about that. One second. This is not trivial to me. I have to kind of think about it a little bit. Okay, so let me grab this. Okay. So what we can do then is we have our r squared here, which we just found as some sort of double distance. Then let's see. What we could do is we could say, here. Yeah, so we could find some sort of ratio. We could say x squared. Dagnabbit, let me think. It's a super muggy day outside, by the way, guys. I don't know why, but it is super muggy. It's like dark and all like, I don't know. It's like, meh. Anyway. Okay. So what do we need to do? We found the acceleration. So we have r. And what we need to do is find x, y, and z. See, that's the thing. I was imagining the gravitational force between them. It's automatically just some r that we have to deal with. I'm trying to figure out how to normalize the distance vector here. One second. I'm for some reason drawing a huge blank, and I can't seem to think about this. So we have the vector there. We have x, y, and z. So it should just be, one second. It should just be, what is it? We have the acceleration. So we'll say acceleration squared. Then we're going to do, I think, What is it? X squared? X hat? 1 second, let me think. Is it X squared? V over length of V? Yeah, I'm trying to think here. Dag nabbit, I can't think. For some reason, I'm just doing very bad with anything to do with vectors right now. So let's pop over here. 1 second. Normalize. Okay, so we have left-hand side. Okay, well that doesn't help any. Length of left-hand side. Okay, so let me think. So we have a vector. Let's go up to the divide. Let me see what that one does. Should be up here somewhere. Divide double right-hand side. Let me see. So we do invert is 1 over right-hand side. 1 second. So we have AV is A times V. Yeah, that's right. Okay, and how do we find length real quick? The dot. Square root of the dot. Okay, that's it. You're right. Good, we're done. Square root of the dot. We're set. Okay, makes sense now. Okay, so what we're going to do is we're going to find the double acceleration there. Now, what do we have? We have distance there. And let me see. Length, I think, if I remember correctly. Let me go up here. Length there. Yes, that's exactly what we want. So here's what we're going to say. We're going to say something like this. So let's say part dot p plus equals. Sorry about that. That was probably super annoying for you guys. Again, I apologize. I guess it just goes to show that everyone gets tripped up with a whole bunch of things, and I get tripped up with everything. So then we'll say the length between the two guys that we have here. So this is going to be part dot position, and I guess it's just part dot p. Then current center mass. Okay. So do the length calculation there, and then we multiply this by 1 second. There's a length. Length returns double. No, length. Oh, length does return a double. Dang it, that's not what I want. 1 second. Let me see which one does the difference between the two. Oh, maybe we don't need to do that. Maybe we can do it this way. 1 second. So we have the two positions. So let's do this. 1 second. Is it distance? No, distance returns a double. Length returns a double. So let's just do this then, because I'm actually not sure what to do here. So we're just going to say particle position. So we're going to say part dot p minus current pointing to p. Yeah. There we are there. Okay. So it's going to be equal to this. And then what we want to do is multiply the acceleration times part p, and then we divide this by what's the difference between the length? Length is that, distance is that. So I guess you already have the normalize function, right? It returns a vector. So maybe we can just do this. Maybe we could just do, oh, I think we still need part. Normalize. Something like that. You're right, it is acceleration. There we are. Let me see. One second. Okay. So I guess I'll go up here. Distance there, theta 2 there. So wait, is this calculating things? Okay, that's fair enough. R there. But I don't think that's right. Oh no, maybe that is right. Yeah, you're fine. Divide by R should be okay. I think. Yeah, okay, that should be fine. Sorry guys, it's taking a while. Okay, so now we do else down here. And then we just do RK search. Oh, I guess we're gonna have to go through all the particles children's. So we're gonna say for child, auto, child, in, then we'll say current dot children. Here. And we will say, 1 second, RK search. And then let's do node children, so child, theta, and part. And that should be okay. The sign of my distance vector is wrong. Oh my gosh! What just happened there? Double R is equal length of d. That's fair enough. That's exactly what I have. Particle plus equals acceleration times d over r. 1 second. I don't have to store it in a separate variable, I don't think. I think this is fine. Doing what I did. Is that not exactly what I had? Let me see. Particle p. What happened to chat? 1 second. Okay. So double G, acceleration, center mass, RR, acceleration times particle minus current P. So you're saying this is backwards. Let me think. No, but storing in a, wait. That doesn't make any sense. If I stored this in a variable, I would have to do the calculation over and over and over again, right? It's one calculation that we're missing. 1 second, let me think here. So we have R. We need R. That's fine. So we're gonna have to calculate the distance no matter what. That's fine. We go theta 2. I'm super confused here. How would storing it, if I store it as a variable, I have to store it as a variable down here. So we'd have to do another freaking double vector D is gonna be equal here. This is what I'm confused about. So you're saying do this, part.p minus current pointing to p, right? So, unless you want me to do it up here, which is also fine, but... I mean, okay. So, you want me to do vector distance is going to be equal to, 1 second, part.p minus current pointing to p. Okay, and then we say double R is going to be equal to D. 1 second. I guess you want length of D. Something like that. And then you want down here this to be D. The vector should be pointing from the particle to the center of mass. Let me think. So we have the particle. Let me think. So gravitational force should be... Yeah, you're right, because there's a negative in there. It's negative GMM over R squared. Yeah, okay. Here. Okay. Okay, so I think then... Oh, that was an equal sign. Okay. That took significantly too long, but I think this is right now. So basically you guys wanted me to miss like one calculation. That's all I'm seeing here. But that's okay. It helps a little bit. So let's see, vector D, current position, particle E, especially when we're doing this a million times, which we probably will be. Yep, I figured out the equal sign. Thanks, Addison. So say double R length D. Let me see. Yeah, that should be okay. Theta 2, current box divided by R. Did I miss something else, Addison? Yep. Yeah, you're right. I mean, you guys are right, especially when we do this a million times. This is great. I probably want 1 over R instead of R. Yeah, that'll save time. Yeah, you're right. So let's do 1 over, and let's say inverse R, just so I don't get confused. So we'll multiply this by inverse R, and then we'll go over here, and multiply this by inverse R, acceleration times D, times, 1 second, inverse R, and then up here we'll do times inverse R squared. Now let me think about that R squared thing you mentioned before, Addison. So if we do inverse R squared, yeah, you're right about that too. Let me think. Okay, so we could probably pop this down here. Grab this. Grab this. D. Wait a minute. DG. Yeah, this is about what I have. Okay. So these are all doubles. Okay, so what are we actually saying here? We are saying okay, let me think. Is this right? Double acceleration is G times current dot center mass dot mass. Put the D in front. Let me see. Okay, sure. I'm actually not sure what the D in front will do, though, honestly. How it differs. So let me think about that one. D times G. Wouldn't it make more sense to put the D in the center mass at the end? Because then we do all the doubles at the start. And then we do the vector stuff at the end. Oh man, we spent the whole day working on this. I feel kind of bad, but that's okay. We got a lot done, and we still have another 30 minutes, so we'll see how far we can get from there. Okay. For the doubles in brackets, what you would have done, vector times scalar times vector, which is 2 vector multiplications. Yeah, so does it not make more sense, and maybe I'm misunderstanding here, but does it not make more sense to put these at the end? Cruel Kitty, sorry about that, Cruel Kitty, I can do that one. I am doing cold atomic physics, so this is, like, Bose-Einstein condensation is what I work on in particular. The idea is that you take a whole bunch of bosons, which are basically atoms with even spin, you cool them down. As it is, not as good. Fair enough. You basically cool these atoms down to basically absolute zero, and then the idea is that as you cool them down to absolute zero, you they become basically superfluid, and I manipulate that. Koakuo, yes, space trees, we're working on it. As it is now. As it is now is good. Okay. Even though we're doing a vector times a scalar times a vector here, D times G times current mass, I feel like, whatever, it's fine. It doesn't matter to me. Okay, so we have the RK search tree finally done, I think. So here's the idea. We go through each of the individual nodes. We check, basically create a new theta value for each of these nodes. No, I know mass is not a vector. That's... Oh, crap, you're right. Yeah, I'm sorry, you're right. For some reason, I was thinking center of mass was a vector. I don't know why. Okay, so we do... yes, so we go through each of the internal nodes, eventually making our way to the external nodes, and we calculate the, basically a new theta value for each of these positions, for each of these nodes. This new theta value is compared to the theta value that we read in, which is going to be some sort of threshold. And then we just say if we are below that threshold, yes, so if we're below that threshold, then we don't count anything more in that tree. That internal node is done. That's as far as we go down. And we calculate the new acceleration for that point. Otherwise, if we're still above the threshold, we keep calculating things until we're below the threshold. Now, let me make sure this makes sense. The theta value. Either put d at the end or put the scalar multiplication in brackets because associativity of times is left to right. So you want me to do this. Something like that. Right? Let me know if this is wrong, but I think that's what you mean. But yeah, that's what I was saying before. I think we should put d at the end. Not that it really matters that much. I guess it does kind of matter a good bit, but that's fine. Okay, so again, that theta value is defined as so. New page before. We will say the following theta is defined as s over d, where s is this guy here, and d is this distance here. There. It's 6 a.m. here in Palua. Where are you at? I'm in Okinawa, Japan. It is 6:37 in the morning. So we're basically in the same spot. Okay. So what do we do here? S here, D here. So what are we saying? We read in some sort of theta, which most people read in as either 0.5 or 1 or something like that. And the idea is that if we have an incredibly large d, we're super far away, we ignore things that are super far away. So as theta goes down, that means we're either super far away or the particle we're looking at is very, very small. And we want to ignore it. So we calculate it if it is below that value. Yeah, I think this is fair. I'm going to put less than or equal to, but it should be okay. This means we dip below the threshold at times, but I think this is still okay. Okay, let's write this. Let's go over here and just compile it real quick just to make sure we haven't made any too big, haven't made too many mistakes. And now let's look at it. So 368 is one mistake. Here we are. This needs to be changed just to particle. Next, RK search passed argument 3. Yes, I needed and 391. We need to change this to an arrow. Maybe you should make the theta a global constant rather than a function parameter since it isn't likely to change. See, here's the thing. I don't know if it's going to change or not. I feel like it might. Oh, that's super frustrating. That is super frustrating. Let me think. Is there a situation where we would run this and we would want theta to change? You know, that's actually a good question. I was thinking about this yesterday. And maybe there is a situation where we would run this and we would want theta to change. What if we are in the middle? Like, what if our particle is in the middle of this giant mass of atoms, you know? Or not atoms, but particles. So, like, it's in the middle of this cloud. No, I guess you're right. Maybe you're right. Yeah, let's do that. Let's go to the top. Let's do constant double. The song is, let me check. It is The Beautiful Machine. California Lullaby by Josh Woodward. All of the music is available directly under my stream. There's a link to all of Josh Woodward's music. But I do speed up the songs by 1.5 times. So it is, again... One second, I have to find it. Beautiful Machine, California Lullaby. Josh Woodward, right here is a California Lullaby. Good. Okay. Sorry about that. So what are we going to do next? Constant double, let's call it theta. Oops. 1 second. Double, theta, and we'll put it all caps. It's going to be equal to 0.5 for this simulation, should be okay. And we'll modify that as we go. So we have to remove theta from here, and let's see, less than or equal to theta, all caps. Also just realized that you can change the gravitational constant, the Coulomb's constant, to simulate charged particles. You totally can. Yeah, in fact, my previous work that I did at Auburn University did that. Yeah, so I mean, it's basically the same thing, right? Just with different forces, which is kind of neat. In fact, there are some other cool things that we can do with this, which we'll kind of get into later. So let's not read in theta anymore. Where are we here? Theta here. So we don't need it for the RK search, nor do we need it for force integration. So we can remove it there. And we can also remove it here. Okay, which makes the force integrate rather simple. So let's go down to the force integrate function. Here we are. Remove theta. And then we can also remove theta from this guy in here, RK search. I can remove it from down here too. Okay, so let's run that just to make sure it currently compiles, and then we'll go from there. So let's do G++. Okay, theta's not declared in the scope, that's fair enough. Okay, so let me change a couple things. 395. I don't know what I was thinking before. Let's change this to an arrow, and then we want to do theta here, remove that theta. By satellite. Hey, Sim. Hope you're well. How long are you planning on streaming today? Honestly, I've got about 20 more minutes left in the stream. I always stream from 5 to 7 o'clock a.m. Japanese Standard Time. That's when I stream. I've got a lot of work to do outside of stream, so I kind of have to, you know, do a whole bunch of different things. But yeah, so I stream same time every day, 5 to 7 o'clock a.m. Thanks for coming in, man. Okay, so let's go ahead and write this, make sure it compiles. Sure does. And now we have 20 minutes left to implement the RK4. We could probably do it, to be honest, but I need to check a couple of different things first. So let me go up to main. Here we are there. We have particle output. That seems fine to me. What I want to do, octree output, we need to think about something. We have the force integrate function. I guess what we need is some sort of general loop, right? So we need some sort of time loop that goes through a simulation loop. So we have octree output, particle output. What do we have here in main? We have ST vector pvec, which is creating a random distribution of particles. Seems fine to me. We output a couple of extra lines just because I feel like it. Why do I do that? I don't know. Let me run a.out. 1 second. I now know why I do it. STD vector particle pvec create random distribution. So in create random distribution, I output things. Let's not output things and create random distributions. 1 second. So where's the C out? There it is. Let's not output here. I don't think we need it anymore. And of course, divide octree. Wait a minute. Let me go up one more time. Main, C out. So we probably don't need to see out very many things anymore, because we're fairly confident that the octree is being created correctly. Let's go ahead and remove all the unnecessary C outs. And by remove, I just mean comment them out. Okay. What's next? C out here, C out there. Depth first search. Yeah, we can remove this one. We aren't actually using depth first search in this particular algorithm, but that's okay. So let me compile it one more time. Oh, 162. Here we are. Over here real quick. I don't think Vectician is a... I'll look. I don't think I have Vectician in the code. Let me see. Vectician. No, okay, good. I might have said it then. My apologies. A.out. We're still outputting something. What the heck are we outputting? Let me check this one more time. See out? There, there, there. All those look commented out to me. I bet you I have a printf statement. Bet you I have a printf statement. Vecticians. 1 second. Vesish. That one I did. Positions. Yeah. Let's go to printf. Oh, by the way, guys, I looked it up. I looked it up the other day. So the difference between the printf and cout functions are actually not that big. I did definitely look this one up, and I can provide for you guys a link if you want. But as long as you're printing out information with the cout statement and you're not using std and line at the end, they're actually roughly equivalent in terms of speed. This is just from what I found online, so, you know, it was like a Stack Overflow post, so there's only so much you can really do there. Okay, good. Seems to be fine. Seems to be fine for me. Okay, so in the last 15 minutes, let's just go ahead and run this function that we just created. So we have all the nodes being generated. Let's go down to main. And I might need to split this up into a header file really quick. Printf implementations actually, in my opinion, or at least from what I understand, are rather quick. But maybe I'm wrong there. So let's see. I want to do the force integrate. So let's just let's do it here. So we're going to say force integrate with root. Let's do g++. A.out just to make sure it runs. It does run. Now, is it correct? I don't know. This will take some time to think about. So let me go down to force integrate. Okay, down here. And in the last 10 minutes, let's just go ahead and create a makefile and kind of do some housekeeping, I think. I think that's a good way to end it. So force integrate, going through all the particles pvec. This has not been implemented yet. We'll do that tomorrow. Now, defining a few variables here. Vector d, current p. D is distance. So we'll say distance. And inverse r. Save those divisions. Divisions. There we go. Okay. Good. Then down here, what are we doing? It's going to be distance. This is actually kind of hard to read, so let me go ahead and put in a quick comment here. That I'd rather use printf style than stream. Fair enough. So what are we doing here? We're doing the distance. This is just a is going to be equal to gm over r squared. I'm just writing that out so there is no confusion here. Where... 1 second. Is this correct? R squared. D. D is a distance. Acceleration. Oh, and then we're going to multiply by the normalized... I'll say norm of r. There we go. That's what we have here. Yep, that's right. Good. That's set then. Now for the arcade search, and then I'm just gonna very quickly put. Yeah, it depends. So I definitely printf is used all the time in my research code, but I don't use it very often on stream, and I don't know why. Again, I'm not very good with printf though. As I mentioned a few days ago, I always forget, and I always have to have like a note on the side of what I need to put out. I don't know. It's used all the time in research code just because it's C. Probably have the fixed type safe printf implementation. I see. Okay, so let me say if above threshold theta. Yeah, I'll get to that in just a second. If above threshold theta, then search again. It does look like R. Yeah. So that extra r is for normalization. So it is GMM over r squared, or GM over r squared, times the distance, which is d over r again. So that's the idea here. And the d over r is the normalization, as Edison said. Okay, so let me go ahead and CP a makefile over here. And let's get that makefile out done. Yeah, so we put the d up front because it saves a little bit of multiplication time. So let's go ahead and CP just a random makefile that we've made before. So I'm just going to do the Huffman makefile because I'm... Oh, no. I got this. Because we're going to have to use this OpenGL later. Let's just grab this one. Search again. Thanks, Edison. Let's grab this. And then pop over here. So I'm going to grab tests. 1 second. OpenGL. And then the makefile from that and bring it over here. Because this way, because we're going to be using OpenGL in a little bit, we have everything else here. Implementing standard compatible printf should be a mandatory lesson for every programmer. Yeah. I'll open this one up. Okay, so let's open up the makefile. Here we have simplegl, simplegl.o, simplegl.h, and shader.h, simply because this is what we were working with before. Now let me go down here and let's change things up for the Barnes hut. So this can be /Barnes hut. The bins is not going to be simplegl anymore. It's going to be Barnes hut. And we don't have an h file here, so let's go ahead and create barneshut.o. Good. Let's remove this. And I guess we don't have anything .h, do we? Oh, we have vector.h. Don't we? We go to the top. Yes, we have vector.h. Let's go to vector.h. Okay, let's see what happens if we just make this. Did I do something wrong? No, I didn't. Woo! So just make sure everything worked right. Let me go ahead and remove star.dat. Oh, oops. Don't know what I was trying to do there. Star.dat. Okay, now let's run it one more time with our make command. Make clean. Make. Okay, and we will say the following, running the last new plot command. And here's our awk tree that we have generated. Seems good to me. Good. Let me see. But overall, its structure is hard, and it teaches a good lesson about bad standards. Yeah. How much school do you have left until you get your PhD? Right now, it's just research, so no school left. By that, I mean it is pretty much exclusively just whenever I finish, I'm done. However, I have 3 more years of funding left. Definitely. And honestly, I don't see any reason why I'd want to leave early. I mean, I like this place a lot. I mean, this is fantastic for me. Like, the best place I could have gone to for me. So, at this point, I'm just kind of chilling and, I mean, obviously working hard, but I'm probably gonna have 3 more years left. Maybe 2, depending on how fast I want to finish. Okay, so now we have that, Control D. And guys, I kind of feel like I want to move all this into a header file. Yeah, I kind of feel like I do. We got some free time. I misspelled function so many times. There's another misspell of function. No, wait, that one's spelled right. This one's spelled wrong. 1 second. There we go, function. Good. So we'll call that there. What do you guys think? Should we turn it into a header file? What other functions do we have to implement? We have to implement enough. Let's go ahead and put it into a header file. So let's go into vi barnes hut.h. Let's go ahead and start the file up. Something like that, barnes hut.h. And I think this will be it for today, guys. We've done a good bit. Maybe didn't get as far as I was hoping, but hey, that's life. Barnes hut.cpp. Okay. Now luckily, because of the way I write my code, this is actually going to be relatively straightforward to make. 1 second. All we have to do is up at the start do an if and f, and we'll define barnes hut h, and then we'll do a define. I forgot a guy there. So we'll do define. That's not how you spell define. That's not it either. I got all the letters right, but everything else is wrong. So we'll do define Barnes Hut H. Then of course we need an end if at the end. Okay. Now all we have to do is copy all these the inner guts here over there. So let's see, what do we have? I guess we'll just copy all this over. So if I have this correct, we should just be able to copy this down to here. Paste it over there. So that was through the node struct. Let's go again. Then we grab all these. There we are. Grab that. Paste it over there. Oh, oops. That was a mistake. There we go. That should work okay. Let's break and quit. Let's go ahead and comment it all out up there. 1 second. And let's include... what do we want here? We want Barnes Hut.h. There. Comment all these guys out. Just to make sure it works. And then we should be good to go after updating the makefile. Let's go over here, vi makefile. And let's add in a Barnes Hut.h. Rank quit, make. Let's see how it breaks. It totally does break. Include does not name a type. Vi Barnes Hut.h. Make. Include does not name a type. Oh, dagnabbit. Make. Alright, let's see what happens. There we go. That one seemed to run. Good. So now we can remove all these lines up here. Let me really quick do a set number. Looks like it is 108. And we're going to go up to line number. I don't know what happened there. So let's just go ahead and remove all these guys here. It's a more efficient way to do that, I'm sure. Okay, those guys are removed. And we can also probably remove all these real quick. Let's do that. Just to make sure I'm not being an idiot. Now let's make that. Good. Okay, let's remove it over here. Okay, last thing to note before we end today's stream. Do you guys want me to commit this to GitHub? If you do, I can. Otherwise, I will not. Just because it's not fully done yet. I wanted the RK4 stuff to be completely finished before committing it to GitHub. Okay, so let me see. Make command seems to be working. Just to be clear, let's go ahead and remove start.dat one more time. Should be okay. Make it. We're in the last new plot. And Octree seems to be generated just fine. Good. Okay, I'm not seeing any comments on the GitHub thing yet. So what I might do is I might leave it off of GitHub for now. Let's Control D. Let me run a quick git status. And let's see what we got here. Seems good to me. Barneshut.h. Barneshut.cpp makefile. Okay. So let's see. What do we have to do left? Okay, so we have to implement the actual RK4 stuff. We will do that tomorrow. However, I'm quite happy with how far we got today. Even though we only really wrote a couple lines, we have done a recursive search. We have now updated the accelerations just fine. Now it's up to us to go from that acceleration that we've updated to actually changing the particle positions, and we'll go from there. After changing the particle positions, we then have to take a step back and work on some OpenGL stuff. And I'll be honest, guys, OpenGL is not, it's not hard, but it's not easy. Maybe you're right, Gus Jordan, but it was just from the stats that I read. We can take a look at that too later. It doesn't matter that much. We'll kind of hop back and forth between the two anyway. Yeah, so you're probably right. It was just, I looked it up online afterwards, and they seem to say that, let me see. There was something, I just Googled it, I think, printf cout And it's probably the first one. Probably this one. 1 second. No, this isn't it. I don't know where it is. But yeah, that's definitely something we can worry about later. Frank, I'm not ignoring you. You asked one question, which is whether Gustorm was gone, and I didn't know the answer to that. Anyway, guys, it's 7 o'clock in the morning. That's about the time I typically end my streams. Again, we have some stuff left to do. A lot of stuff left to do. Let me see. Double output should be about exactly fast. Printing in double itself is fairly slow. Yeah, so I'm not sure. We'll take a look at this later. But this is about it for today, guys. Again, we got pretty far. We have a lot left to do. When we start hitting the OpenGL stuff, it's going to feel like I'm hitting my head against a wall, and you guys might not like that very much, but we'll see how far we go. Tomorrow we'll be implementing the RK4 stuff, and we'll go from there. And actually, today is Monday for me, Frank. I'm going to work in, like, I don't know, actually, like, right now, because I have, let me see. I'm going to be swimming tonight, so I have to kind of leave work early a little bit. So I have to get into work a little bit early. Anyway, that's completely beside the point. Thanks guys so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simulaos. Yeah, work, I do research for work. That's what I do. I mean, I get paid to be here as a student, so I consider it work. Anyway, that's about it, guys. Thanks so much for coming in, and I'll see you next time. Bye, guys.